Compute the curl of the rotation field defined as vector f is equal to the cross product of vector a and vector r, where a is the vector in the x direction 1, 0, 0. We call this the axis of rotation. And then we have vector r is defined by components x, y, z, which is our position vector. So we're asked here to find the direction and magnitude of curl as well as sketching a graph. So thinking about what we're given here, we have our axis of rotation, which again is defined as vector A, and that's 1, 0, 0. We can even just write this as I hat. So it's in the x direction. And then we've also got a position vector defined as r is equal to x, y, z. So what we want to do here is find the magnitude and direction of curl, and the goal is to show that the curl of this rotation field is going to be in the same direction as the axis of rotation. So the first thing that we want to do is find the rotation field. And again, that's given to us here. We have that it is defined as the cross product of the position vector and the axis of rotation. So vector f is A cross R. And we'll put this into our 3 by 3 matrix. I hat, j hat, k hat. Vector A is 1, 0, 0. And vector R is x, y, z. So finding the determinant of each one of these components, we use that crisscross multiplication, and this gives us 0 times z is 0 minus y times 0 is 0, I hat, minus 1 times z is z, minus x times 0 is 0, j hat, plus 1 times y is y, minus x times 0 is 0, k hat. And so we are left with 0 I hat minus z j hat plus y k hat, or we can put this in its component form as 0 negative z y. Again, this is our rotation field. So we'll want to include this on our graph. All right, so now that we have these vectors, these rotation fields components, we're ready to go ahead and compute the curl. So we know that the curl of a vector field is defined as the cross product of del and that vector field. Right, we can remember, actually, let's put this right into our 3 by 3 matrix here for simplicity. So again, we have I hat, j hat, k hat, and then del is the vector containing the indicators of derivatives. So we're taking the vector operation of taking our partial derivatives here, dx, dy, dz, and then vector f is the rotation field we just found. So it should be 0 minus z y. And then again, applying the determinant, our crisscross multiplication, we have the partial derivative of y with respect to y, which gives us 1, minus the partial derivative of z, or minus z with respect to z, gives us negative 1 I hat, minus the partial derivative of x with respect to y, which is 0, minus the partial derivative of 0 with respect to z, which is also 0, j hat, plus partial derivative of x with respect to z is 0, minus the partial derivative of 0 with respect to y is 0, k hat. And so therefore we can say that the curl of our rotation field here is going to be 1 plus 1, which gives us 2 I hat minus 0 j hat minus 0 k hat. Right? Or we can, if we put this into our component form, 2, 0, 0. And so maybe we're observing at this point that, hey, we have a scalar multiple here of our axis of rotation of vector A. This is 2 multiplied by vector A. So this is indicating us that it's pointing, or the curl is pointing in the x direction. Concluded that this is points in the x direction. And then based off of our scalar multiple here, we can see that the magnitude of our curl is going to be twice that of the magnitude of vector A. And so we have the magnitude of the curl of our rotation vector field is equal to the magnitude of 2 times vector A. So we could just pull that scalar multiple right on out. So we have 2 times the magnitude of vector A. And of course, vector A has a magnitude of 1. So the magnitude of our curl is simply 2 units. All right, so let's go ahead now and sketch ourselves a graph in space, observing what's going on. Right, so we have our z-axis, we have our x-axis, and we also have our y-axis. And so we'll say there's 1, here's 2. And so our axis of rotation is indicated by vector A. Again, vector A is defined as the vector 1, 0, 0. And we just discovered that the curl of this rotation field is pointing in the same direction as vector A. So this is the curl of that rotation field, vector F, which is 2 times vector A. And then the rotation field, which is defined as vector F, and we found that to be 0, negative zy, is going around the axis of rotation here. So we'll indicate this with red arrows going around the axis of rotation, around the x-axis. So all of these little red arrows are part of that rotation vector field.